What I'm going to talk about is Tern. This is a project I made, which is a static analyzer for JavaScript code with the explicit, precise purpose of improving editor assistance and integration. So it's not a type checker, it's not a linter. It's, though it does, its main task is type inference. That is for editor assistance purposes. So it has a very different design than what you would see in a type checker or related thing. I'll start with a very quick demo. So it does things like auto-completion, context sensitive. So let's say window, it knows what window is and what you can complete there. You can ask it about docs if they fit on the window. It does basic, very basic refactoring things. So if I have a variable here, I can just rename it and it knows about scopes. So these are absolutely trivial things in static languages that we've had for, I don't know, 15 years, maybe more. They are rather hard to do in dynamic languages. There are other systems like Visual Studio which have pretty good JavaScript analysis built in. Tern is supposed to be an editor-independent component. It's open source and improves the situation for the rest of us. So what I was inspired by is the Emacs programming environment for Common Lisp, which has extensive, for example, jump to definition, and you see a list of function arguments when you're typing arguments, and these are giant time savers. You don't have to go hunt through the code to look something up. It just implicitly does it for you and gives you the context that you might be looking for. In the Common Lisp world, or Clojure and all Lisps pretty much do this. What they do is have a running image which has all the code loaded, and they talk to this image through some protocol to get the feedback they want. And this image, so that this runtime obviously knows about the code. It loaded it, it compiled it, and it can answer these questions. JavaScript implementations do not do this, so we need a different approach. Tern is basically a process that runs alongside of your editor, doing something like that, slurping in all your code, analyzing it, and answering questions about it over a simple HTTP protocol. It's written in JavaScript, so for JavaScript-based editors, you can actually embed it directly in the editor rather than as a separate process. So the reason why integration for dynamic languages has lagged behind is basically that they do everything in their power to make life hard for static analyzers. So obviously the types are dynamic, so there is no formal algorithm for deriving the type of something when you just have the source code. Then many of them, especially JavaScript, has very ambiguously typed primitives, so you can pass anything you want to plus, it'll do something with it. Similar for the built-in functions. You can give them anything, it will convert it to what it happens to like and do something with it. So you can't use a type inference algorithm that starts from uses. If you see a plus 1, that doesn't tell you that a is an integer. So you have to go the other way around. You have to see what kind of values flow into a from the rest of the program. And then, of course, JavaScript can manipulate types at runtime, which is a whole different class of horrible in terms of static analysis. There is some research on sound analysis of JavaScript code. This research tends to start by defining a subset of JavaScript that they are going to work on. So things like eval can not only execute arbitrary strings as code, they can also change the scope chain in JavaScript and do lots of horrible things. Soundness is explicitly not a goal here. So that allows us to do much cheaper, faster, and simpler analysis. The goal is being helpful in the face of non-weird code and doing the best we can when the code is weird. But there is no worry about getting something wrong. Yes?
So you're saying faster analysis. How is it compared? Oh, sorry. So you're saying faster analysis. How is the performance compared to, for example, what we know, like statically typed languages for Java or some stuff like that?
So I don't really have enough experience with static analysis on these languages to say much about it. I can say that on my laptop, Tern slurps through about 10,000 lines a second. So you do have to cache. You do need this running instance. You can't for every query start an analysis from scratch. But it is real-time interactive if you have most of the information already in your image. And then
okay, so if I'm a Java developer, as I am, and I start doing something in, for example, Eclipse, and you have Eclipse support, I think.
I think someone wrote a plugin. Yeah. I can't vouch for its quality, or I haven't looked at it.
So there is an additional, there's some additional stuff like communication going on. So is it still in the line? Is it still the same experience, the same real-time experience that I would have in a statically typed language?
Yes, there are some situations where you notice a lag. For example, if you jump to a definition in a file that you recently changed and hasn't been fully reanalyzed, it forces reanalysis because it needs the exact character location of the thing you're jumping to. But these are relatively rare. For the common things like completion and jumping to definitions in known files, it's instantaneous. Okay, so you mentioned that somebody wrote an Eclipse plugin. Are there other IDEs that already support it? The things that I support are for Vim Emacs. Sublime Text has a good plugin. There are some editors that come with it out of the box, like Adobe Brackets. There's a plugin for Atom. But these are most of the classical text editors. I don't really know what the situation is with IDEs. I think someone wrote an IntelliJ plugin. No, I haven't really, there are a bunch of GitHub projects, but the fact that someone creates a project doesn't mean that it actually works, so. Okay, thank you. Okay. So, it seems
on the topic of IntelliJ, how does the quality of the results compare to other analyzers like the one in IntelliJ that builds up?
It is definitely better than IntelliJ was in 2013 when I played with it and wrote this. It's the best implementation, I think, now is what Microsoft have done. I'll come back to how they're doing it. They usually beat Tern, though there are situations where their approach doesn't work so well, but maybe they've improved. It's also been 2 years since I played with that. There are situations where Tern beat it, but I think on the whole, Visual Studio is a bit better.
And what's their speed compared to Tern?
Good. I didn't notice serious delays. And then there's, of course, approaches like Flow and TypeScript, which are also kind of in the same, a very different approach, but in the same vein. They actually type your code using annotations, and thus they can actually give accurate information opposed to guessing from the vague semantics.
Just as a small comment on IDE support, it's very difficult to combine Tern with the built-in functionality of something like IntelliJ. So you would have to either choose between having Tern running in IntelliJ, and that would mean losing all the advanced features that IntelliJ has, like refactorings that Tern probably
so
doesn't
probably
provide.
Poor fit for that.
Yeah. Or you could just use the built-in stuff.
Yeah, this was born basically out of frustration of their existing no decent Emacs support, and then some other editors in a similar situation kind of hitched along on that. But yeah, in IDE style editors, I haven't seen that much use. So it's the algorithm I'm using rather directly is ancestor of the inference algorithm used in the SpiderMonkey JavaScript engine, where they use this for a very different purpose, namely more more compact and efficient code generation because if you know the type of something, you don't have to do type checks and weird polymorphic interpretations. So there they need to be conservative, only draw conclusions when they're absolutely certain, or you get a seg fault, which is very different in Tern, where it's great if you can guess some type for something that you otherwise couldn't tell anything about. Patrick Welton wrote a fork of JSC tags where he applied this algorithm for something similar as what Tern is doing, and I kind of took inspiration from that and built Tern on that. So what I'm doing is a form of abstract interpretation where I just parse the whole code and run over it. And the product of this interpretation is a graph connecting, basically showing the way types flow through the program. So also something like data flow analysis. This graph that I produce has something called abstract values as nodes. These are basically corresponding to a given variable or property or other location in the program that might have one or more types. So if you have a variable x and you assign a string to it, then the abstract value corresponding to x will be noted to contain a string. And then the edges in this graph are paths through which types flow. So if y is assigned to x later, then that means all the types in x end up in y. And we create an edge to represent that fact.
Sorry,
So here's...
excuse me, but how do you do the incremental patching? How can you use incremental patching? Like, because you mentioned that it's very important. I mean, incremental changes.
Right, so the editor talks to the Tern instance over an HTTP interface, and when it makes a query, it can include the file that changed, or in case of huge files, a fragment of the file around the change. The editor knows what you've been typing in the meantime, so it knows which files are dirty, so to say, which files Tern doesn't have an accurate view of. It sends that along, and Tern then analyzes this file in the context of the whole project that it has analyzed beforehand, and then runs a query on its resulting representation.
So you just do it one per file, right? You don't do incremental sort of like changes. I mean, if I change like tiny function, for example, you still parse the whole file.
For small files, yes, because it's simpler and more reliable. For huge files, say over 3,000-4,000 lines, we actually only analyze a part around the change and then fix that into the scope that already existed in the... That works relatively well, but has some flaky edge cases. So, yeah. So here's an example. Is the code entirely visible? Yeah, sort of. So here's this trivial program where you have variables x and y, and it is obvious that they both have type string. If you add another statement, they actually get a union type of two types. Actually, this wouldn't be the case because y would end up a Boolean, but one shortcut that Tern uses is that it's completely oblivious to flow control. In this case, flow control would be trivial to handle. Once you have functions which are called anywhere and do something, it becomes very expensive to handle. And most sanely typed programs don't reuse the same location for different types in different phases of the program. So this is a good enough approximation. So this is the graph that we built for this. The orange things are abstract values, which can have 0 or more types associated with them. And because x is assigned to string literal, we let the string type flow into x, and now it's there, it's written under x. Because y gets x's value, we create a link between x and y, and that means the type that ends up in x also flows through to y. And then of course if you add another type, it also flows through the same path, and you get the expected types for these two variables. Then we'll go through a more advanced example involving an actual function call. So say we're interested in the type of R. We call here f with two strings, and f concatenates them and returns them. So we want R to be inferred as being a string. First we look at the top statement, where variable R is declared. There's a reference to variable f. We haven't seen its definition, but we create an abstract value for it anyway, because when someone defines it later, we want to know that this was actually already used in some way. Tern's analysis is entirely order independent, so you can throw code at it in any order. Also, definitions may arrive in any order and it'll infer the same result. This has many advantages for being able to, for example, analyze a file and then figure out its dependencies and pull those in after the fact. So what we create here is one abstract value for f, one for r, and then 3 for the arguments and the result type of this call. The purple node is an active node, which is a node with a specific kind of code, in this case the code for handling a call. And because f flows into there, if f gets a type, that type will also flow into that active node, and the active node will wire up the function type with the call. So the arguments will be wired up to the parameters of the function. The return type of the function will be wired up to the result of the call. And then we have R wired up to that result, so that when we know a result type from this call, we know that R also gets that type. At the second line, there's a function being declared here. So we allocate a function type.
Hi.
Where? There.
I'm a little bit, what is it that you consider to be a type?
A type is something like a string, boolean, function of integer returning, I don't know, or an object with a given shape.
So what is the shape of an object?
An object, we'll get back to that in a moment, but an object basically is a type object mapping to several abstract values representing the types in its properties.
So do you keep track of the chain of prototypes going on?
Also, yeah.
Okay. So if I go and I add something to the prototype of the root object, then all of a sudden that also gets reflected through the graphs of all of the other types?
Yeah, actually, I don't think I handled changing prototypes, only creating with object.create and new creating that kind of prototype change. So yeah, the function type has references to abstract values for its argument and its result. The body of the function tells us that plus is applied to those, because plus in JavaScript is a bit strange, complicated. We have to define another active node type for that, which looks at its inputs, and if it sees a string, it spits out a string. If it sees two numbers, it spits out a number. And then we let that function type flow into f, from which it'll continue flowing down into the call, which causes that active node to wire up these arguments and parameters in the correct way. So now if we fill in the actual types passed to that call, they flow up into the function's parameters, through plus into the function's return type, into the call's return type, and now we know that R is an actual string. So this is already a non-trivial graph for a completely trivial program. You can imagine that these are impossible to visualize and very tangled for bigger programs. Yeah, go ahead.
So in terms of the abstract interpretation, is it that expressions kind of are evaluated to types, say, vaguely, and then a program is like evaluated to this graph, or is...
No, the graph is built up. Basically, the abstract interpreter gets an output object when it's running on an expression, and if the expression produces a value, that will be propagated into the object passed to it. And that way, and then there's code for when it's seeing a function in the AST, it will wire up a function type for that and make sure that the arguments end up in the scope that's being passed down. So they have access to the scope and their output object, which can be an abstract value or one of these active nodes.
So I guess then the abstract interpretation is not really compositional in the sense that you like abstractly evaluating some expression.
No, it doesn't reduce it to a single
right,
thing.
but you
No.
you mutate some kind of global representation that is the graph. I see. Okay, thanks.
Do you also have a question?
So you said the graph is pretty large, but I mean, how you deal with the very large programs? All my programs are sort of very large because they require a lot of node modules, and then if I parse them, it takes a lot of time. And do you keep them in memory, or do you somehow cache them, or is it?
This is, so there is a mechanism for condensing a library down to just its types and loading that. It's unfortunately not as user-friendly yet as it should be, but this is possible if you load some huge library and you have to, but also when it's tracking dependencies, it uses a kind of, for each dependency, budget, and if you keep from that dependency branching out to more, at some point the budget runs out and it just cuts off the analysis on the assumption that probably the types that you're actually interested in, the direct interface to the module that you're calling, will have been sufficiently determined at that point. But these graphs do get big. For a big project, you might get into a gigabyte or 2 gigabytes of just memory.
Okay, so maybe a subsequent question. Which module systems do you support? I mean, if you require something else, then of course you have to analyze it as well, and then it's maybe not quite easy to see where you get the code from. I mean, if you use something like ES6 modules, do you support that? And then do you support require? Do you support
There is a plugin architecture, and currently there's a plugin for Node and for require.js, and there will be support for ES6. I actually started working on ES6 support, so far it's ES5. And these basically, when you create a server, you give it a mechanism for accessing files. So if you're running Node, this will just be looking at the local file system. But if you're using require.js, for example, you can also require URLs, so it recognizes that and tries to fetch them from the net and things like that. But usually there's a relatively straightforward mapping. For example, Node plugin, when it's running on Node, just uses Node's own resolve mechanism, so that you actually get the file that would have been required.
Okay, thanks.
So speaking of modules and libraries, I guess that for native modules like the DOM or native NPM packages, you have some kind of a summary that says, okay, this is actually how it works and what types it expects and returns.
Right. This condense mechanism that I mentioned before outputs a kind of JSON file, so you can run it on a file and just get a JSON file that succinctly describes the types. And there's handwritten or partially generated for documentation files of that type in the distribution for the browser, for a few popular libraries, and for the language standard itself. So you get those, you just, you load them. There's a configuration file format, just JSON, where you can say which libraries to load in this directory. And I also wrote a shim that takes TypeScript definition files and converts them to this, but because their compiler keeps changing, it no longer works with recent versions of the compiler. It's a work in progress.
So JavaScript is also an object-oriented language, and actually call is a special function, and just like apply. And actually the first argument would be the array of arguments, and then you'd have this argument, and then with apply. So is it this argument like being more object-oriented, is this being also analyzed and inferred?
Yeah, actually, this slide lies a bit. Each function and call node also has an absolute value for the object that's being passed. And yeah, those are just reflected in all function signatures. And you can also just use the call method and pass an explicit object.
So, like in some libraries and APIs that overloaded this, like in a DOM and HTTP, Ajax call, whatever. So you keep track of this and you infer it and.
Right. So it'll in some cases it'll infer it from context. If you're defining a prototype, it'll assume that this will refer to instances of the prototype. For just normal functions, it'll wait until it sees a call to figure out what kind of objects are being passed in as self.
But do you handle something like document create node, where essentially you pass the literal string and return, you have like different types depending on the string literal?
Could you repeat that?
I mean, consider, for example, like document create node or create element, where, for example, you have different types depending on the string literal.
No, those are a nightmare for typing. Those are all treated as one node type, and it has all the properties that all possible node types have. It's almost impossible to do better, because if you do document query selector something with this class, you have no idea what you get back.
Yeah, but I mean, for example, TypeScript, I mean, they sort of try to implement it, because now they support sort of like inheritance, or based on string literals. So in a sense, they treat, for example, like create document node depending for create element depending on a single literal.
Yeah, you could do some things with that. So create element is an example, but you couldn't solve it generally, because often you get them just from some other structure and you don't know what they are. So I've so far considered that not really a great solution.
Okay.
Behind you.
So let me just try to understand a few things. So do you have flow in the heap between fields as well? Between object fields?
Yes, each object property is one of these orange nodes. Actually, let me just skip through to... Here's an example with an actual object. So there's the code. This is the object type with references to its properties.
Right.
And then there's, again, a special node for get the Y property of all objects that flow into this. And that's how I implement object access.
Right. So if that's the case, then essentially what you're doing is kind of morally equivalent to a context-insensitive pointer analysis of Anderson style, right?
I guess. I'm not really
I mean, we build things like that
terms.
and they scale really quite well. I mean,
Yeah.
all you're getting out of it is effectively concrete types at the end, right? But, you know, the technique is pretty much the same.
So the system I subscribed so far works great for monotyped, simple programs. If I have the time, I probably will be able to get into a few tricks that I use to handle simple polymorphisms.
But even one level of context sensitivity will buy you something.
Yeah.
Yeah, so I just had a quick question. Do you understand the closure type annotations? The Google Closure Compiler, I mean, has...
These are JSDoc style.
Yeah, JSDocs,
yes.
exactly.
Yes, I parse several styles of JSDoc comments, not exclusively, because there are all kinds of conventions and they're not that great documented, but for simple things, the types that you annotate will also flow into the graph.
Okay, cool, thanks.
On using multiple sources of type data, the SpiderMonkey type inference had to use solid data, as you explained, but since you can use sort of really shady data, if you have a field that can be type A or B, and then you see it used, maybe called, a method is called on it that only exists on B, are you using that to then decide, okay, this is type B?
No, I don't. I do use something like that in the context if I don't have type information in my graph and you, for example, try to complete a property on something, you really need the type to be able to do anything sane. So what I do there is look at outgoing edges from that thing. So if, for example, it has edges to get y and get z. I look through the known object types. If something matches, it has those properties, and complete based on that type as a kind of fallback. There's quite a lot of interesting things you can do with these graphs. Also, if something flows into another node which does have a known type, then you could approximate its type as the thing that it flows into. So here's, as I said, this works great for monotype programs, but here's a very simple example of something that does not work. You have a generic function last of, which takes any kind of array and gives you the last element, no matter what the type is. If you just use the naive approach I outlined, it'll get a new type in its return type every time it's called. So these would be, both num and str would be number or string, which is not very helpful, and worse, it ends up polluting the whole graph with useless types that don't actually apply. So what I do here is, when a function is analyzed, just its body has been analyzed. We haven't connected the parameters to anything yet, and it does not have a return type at that point. We do a relatively shallow graph search from trying to get from one of its argument nodes to its return node. And if we find such a path, we can derive a function that can compute a return type from the argument types based on that path. And so then we just disconnect the normal return mechanism and use this function to compute the result of each individual instance of that function.
So in other programming languages, you can solve it by having a more maybe powerful type system, where you can describe whatever goes into that function, whatever that array contains in that function, whatever that type is, will be the return type. That might be generics in TypeScript, for example, or generics in Java or C#, but it of course requires a more powerful type system. I don't know how the type system that you're using under the hood looks like, but do you support anything like this?
It's very simple, the type system, and not really something that's usable for manipulation or any serious theorizing. But the mechanism I'm using, and I'm thinking about moving to something more powerful, the mechanism I'm currently using is that functions can just have an opaque blob of code that compute their return type if they are known to be special and return something that we know about, and otherwise we have this normal arrows and boxes mechanism to compute it. And there's a simple text notation to describe these types.
Okay,
thank you. So then you get serious runtime type manipulation. There this trick really doesn't work. For example, many people define all their types using some helper function. A common one is called extend, where you just copy all properties from one object to another. And that, of course, the analysis I outlined completely falls down there. So what I do for functions that I consider type manipulating, I have some heuristics on the kind of things that type manipulating functions do, and I score each function as I analyze its body to how much of that stuff it's doing. If it gets below a certain threshold of type manipulatingness per expression, it flips into a different mode where its subgraph is reinstantiated for every call. This is expensive, and you have to be very careful about recursive calls, and it's very easy to get into an infinite expanding graph that way. But I got it to work, and that means that even things like this and the various subclassing functions that, for example, CoffeeScript spits out, and most of the tools in underscore just end up working. It makes just last week someone sent me a link to a library called something on Lambda with the first letter change. Right, and it's Tern took 20 seconds to analyze that file, which is only a few thousand lines long, because it was all functions ended up being instantiated multiple levels deep, and that was just pretty much exactly the pathological case that it doesn't currently handle. I have to think about some way to just stop rather than freeze in these situations. I haven't quite found the right approach for that yet. But I want to stress that this is rare. Most code just goes through and you really get useful types. Yeah.
So why do you want to deal with computed properties? Seems like you should drop them right away.
Because many people define their actual classes this way, their types, and you do need to know the properties of the classes people are using to give completions.
Constant properties you do. Computed properties, I'm not so sure.
Well,
if you have a constant, that's a different case.
Yeah, but these are, for example, they'll pass in a source some literal object with a bunch of properties, and then copy these to the prototype of some constructor, and then instantiate that constructor to get an object which has all these properties in this prototype chain. And these absolutely need to be known to the analysis, or it's pretty much useless. So what I'm doing here is I recognize this pattern of copying over all properties, and
then you can pattern match.
Yeah, and I have been playing with ideas of modeling small collections of strings, so that I can, in a few more cases, for example, if you use object.keys, Tern is lost, which returns all the keys in an object, because it can't represent an array of these specific strings. It can only represent an array of strings.
So do you do also something like this for higher order functions? Like say map on an array?
Yeah. And that's where the functional library went wrong. It was all higher level, deeply nested higher level functions.
Right.
Okay.
I just want to point that out in case he does have more slides if he actually has a few.
I have a few more, but I already touched on this. So when we don't know the type of something, we just use the graph context to guess. This is very useful if you're writing a library where your project isn't actually calling your functions. And also there's a bunch more magic for inferring this pointers, because those are very critical. The completion is just terrible if you can't complete on this. And usually when you're writing a class, you're not instantiating it yet. So it recognizes some patterns like assigning to a prototype or creating an object literal, and assumes that you'll probably want this. And it has a mechanism to, if another object type comes in as the this pointer, to overwrite and undo these speculative types, which means that we can do it without doing too much damage when we're wrong. So as I said, the server slurps in a whole bunch of files, and you get a cross-file knowledge. It knows the whole project. You can jump back and forth between files. You can rename things across files. If this goes a bit dodgy, if the Tern actually knows all the files that you're using. If you're not using a module loader plugin and you didn't have all the files open in your editor, it doesn't actually know. But you can also configure your project to load all files in this directory or something like that. But you have to be slightly careful there, because if Tern doesn't know some files belong to it, these mass renames won't actually go through. Then you can see here, for example, a weird pattern for defining a module. At the bottom, it assigns to this, which is the global object, creates an empty object, passes it to exports, and then assigns in this anonymous function some stuff to it. This is relatively common in browser programming. But these are all easy for Tern to see through. If I say my mod dot, it knows what it is, and I can also jump to it. The approach works surprisingly well for a lot of code. I was actually skeptical at first, but it's useful enough. So yeah, as I said, there are plugins for these editors, which in some scenes are the major editors, but I guess there are also whole worlds of people using IDEs for which the situation might need to improve. The Tern project file is a simple JSON file saying load these plugins, load these type definitions, always immediately slurp in these files, don't ever load this file, things like that. Then, as I said, a very interesting implementation exists in Visual Studio. What they do is very different, though I think they also have been extending it with some static analysis similar to Tern, but their basic approach is they have their own JavaScript engine. They instrument it to actually run the code, disable I/O, and then look at what happened in the running program to figure out types. So this is, you can, for example, for dynamic type manipulation, this works perfectly. Stuff at the global scope that gets defined in some extremely indirect, weird way, you just get exactly the shape that they have. It does have some problems for functions that aren't really reachable from the current code. If it can't find a path into a function, it can't figure out the types. I think they've started using techniques like Tern or maybe completely different static analysis to improve that situation. But that's the kind of trade-off there. If I had all the budget and time in the world, I would probably start extending Tern in that direction with doing a superficial interpretation run first, and then static analysis using the input from what happened in that run. Because most type manipulation, which is the big problem, happens once at startup time and is actually not expensive to interpret. Of course, then you have the whole problem of writing an interpreter, and that might not be fun, but it only needs to be relatively superficial.
How did you write your abstract interpreter?
I have a parser that I also wrote for JavaScript. In JavaScript, this just spits out an AST. There's a relatively standardized AST format for JavaScript code. And I also wrote a AST Walker framework, which allows you to say, run through the code, and when you encounter such a node, do this, and then you can tell it optionally how to descend into that node. So it's, as I said before, it just passes a goal node to each invocation on an AST node. So a goal node in terms of this graph that I described, so that the result of this expression knows where it has to go. And that is actually not that much code. The inference engine is a few thousand lines. Other related work which I already mentioned is Flow and TypeScript. They both have little daemons that you can run alongside your editor, which will do something like Tern, analyze the whole project, give you very accurate completions, and they have, of course, a lot more to work with because they do have a relatively well-defined type system and type annotations. And that's all I have to say, so if there's a few minutes left, we can gladly do a few more questions.
So to your comment towards the end, I mean, we talk with the Visual Studio guys quite a bit. So one of the ways you can consider doing it is that you can scrape a heap snapshot at the end of once you reach a steady state somewhat, right? And the new browser, Edge, the Spartan browser, actually has some facilities for that as well. And you can do that once the program is run for the first time. You don't even have to artificially execute it in this I/O blocked environment, which is kind of a mess. You can just let until the user runs this thing.
Right.
Capture
then you'll also be somewhat out of date to recent changes.
But I mean, the initialization probably won't be, right? Capture it and then start the analysis at that point. So.
Is another question there?
So it's rather comment. So I played around a little bit with the flow engine, and it works with no type annotations at all if you want that.
Yeah, they also have.
And I guess what they do internally must be pretty similar what you do. So maybe you
I'm actually
talk to
not
them and
sure what kind of they are flow sensitive,
Yes.
and they're implemented in a faster language. So I guess
They do it
maybe,
in hello camel, but
yeah.
maybe that might be a problem. But their algorithms might be influenced by them. I know
Yeah.
that the guy who wrote it is around. The flow.
Okay.
Yes. So maybe you find him.
If I run into him, I don't actually know about there is no real documentation about the algorithm that they use. Just
I don't know
what it
either.
can do.
I just know that it works without type annotations. It's very powerful.
And it's open source, but I didn't bother.
I
to
can't
read
understand
the code.
camel anyway.
I think it's actually built on the PhD thesis of Cormac Flanagan.
So it's, I think, very much oriented after the PhD thesis of Cormac Flanagan, who is actually also at the conference. So,
Also, just as a comment, unless I'm completely mistaken, you can indeed run it without any annotations, but I think that it's way more powerful if you add the annotations, and I think without the annotations it's not all that great, but I'm not sure. That's just what a colleague of mine told me. And unfortunately, I really don't understand why, unfortunately, the annotations are not like in comments, but it's, you have to, it's like JavaScript syntax, so your JavaScript is not JavaScript anymore, which I really can't get my head around. I don't quite get why they don't just support adding like comments to your functions, because that way I could just...
It's more awkward, but yeah, that's one of the design goals of Tern.
Because I mean, most people are probably not going to convince anyone to, hey, let's switch to a compiled language so we can use Flow. So weird, from my point of view, a weird decision, but yeah, that's just me.
In my experience, people are moving to compiled languages anyway for ECMAScript 6 features and so, and then they just, I think currently most widely used compiler from ES6 to ES5 also supports Flow style and TypeScript style annotations. So then you have both in one.
Yeah, okay.
All right, then. Thank you for listening. Tern is supposed to be an editor-independent component that's open source and improves the situation for the rest of us. So what I was inspired by is the Emacs programming environment for Common Lisp, which has extensive, for example, jump to definition, and you see a list of function arguments when you're typing arguments, and these are giant time savers. You don't have to go hunt through the code to look something up. It just implicitly does it for you and gives you the context that you might be looking for. In the Common Lisp world, or Clojure and all Lisps pretty much do this. What they do is have a running image which has all the code loaded, and they talk to this image through some protocol to get the feedback they want. And this image, so that this runtime obviously knows about the code. It loaded it, it compiled it, and it can answer these questions. JavaScript implementations do not do this, so we need a different approach. Tern is basically a process that runs alongside of your editor, doing something like that, slurping in all your code, analyzing it, and answering questions about it over a simple HTTP protocol. It's written in JavaScript, so for JavaScript-based editors, you can actually embed it directly in the editor rather than as a separate process. So
in the line, is it still the same experience, the same real-time experience that I would have in a statically typed language?
Yes, there are some situations where you notice a lag. For example, if you jump to a definition in a file that you recently changed and hasn't been fully reanalyzed, it forces reanalysis because it needs the exact character location of the thing you're jumping to. But these are relatively rare. For the common things like completion and jumping to definitions in known files, it's instantaneous.
Okay, so you mentioned that somebody wrote an Eclipse plugin. Are there other IDEs that already support it?
The things that I support are for Vim Emacs. Sublime Text has a good plugin. There are some editors that come with it out of the box, like Adobe Brackets. There's a plugin for Atom. But these are most of the classical text editors. I don't really know what the situation is with IDEs. I think someone wrote an IntelliJ plugin. No, I haven't really. There are a bunch of GitHub projects, but the fact that someone creates a project doesn't mean that it actually works. So,
Okay, thank you.
okay. So it seems
On the topic of IntelliJ, how does the quality of the results compare to other analyzers like?
Lots of horrible things. Soundness is explicitly not a goal here. So that allows us to do much cheaper, faster, and simpler analysis. The goal is being helpful in the face of non-weird code and doing the best we can when the code is weird. But there is no worry about getting something wrong. Yes?
So you're saying faster analysis. How is it compared? Oh, sorry. So you're saying faster analysis. How is the performance compared to, for example, what we know, like statically typed languages for Java or stuff like that?
So I don't really have enough experience with static analysis on these languages to say much about it. I can say that on my laptop, Tern slurps through about 10,000 lines a second. So you do have to cache. You do need this running instance. You can't for every query start an analysis from scratch. But it is real-time interactive if you have most of the information already in your image and then
Okay, so if I'm a Java developer, as I am, and I start doing something in, for example, Eclipse, and you have Eclipse support, I think.
I think someone wrote a plugin.
Yeah.
I can't vouch for its quality, or I haven't looked at it.
So there is an additional, there's some additional stuff like communication going on. So is it still?
What I'm going to talk about is Tern. This is a project I made, which is a static analyzer for JavaScript code with the explicit, precise purpose of improving editor assistance and integration. So it's not a type checker, it's not a linter. It's though it does its main task is type inference. That is for editor assistance purposes. So it has a very different design than what you would see in a type checker or related thing. I'll start with a very quick demo. So it does things like auto-completion, context sensitive. So let's say window, it knows what window is and what you can complete there. You can ask it about docs if they fit on the window. It does basic, very basic refactoring things. So if I have a variable here, I can just rename it and it knows about scopes. So these are absolutely trivial things in static languages that we've had for, I don't know, 15 years, maybe more. They are rather hard to do in dynamic languages. There are other systems like Visual Studio which have pretty good JavaScript analysis built in. The reason why integration for dynamic languages has lagged behind is basically that they do everything in their power to make life hard for static analyzers. So obviously the types are dynamic, so there is no formal algorithm for deriving the type of something when you just have the source code. Then many of them, especially JavaScript, has very ambiguously typed primitives, so you can pass anything you want to plus, it'll do something with it. Similar for the built-in functions. You can give them anything, it will convert it to what it happens to like and do something with it. So you can't use a type inference algorithm that starts from uses. If you see a plus 1, that doesn't tell you that a is an integer. So you have to go the other way around. You have to see what kind of values flow into a from the rest of the program. And then, of course, JavaScript can manipulate types at runtime, which is a whole different class of horrible, in terms of static analysis. There is some research on sound analysis of JavaScript code. This research tends to start by defining a subset of JavaScript that they are going to work on. So things like eval can not only execute arbitrary strings as code, they can also change the scope chain in JavaScript and do